The foot bone's connected to the leg bone. The leg bone's connected to the knee bone. The knee bone's connected to the thigh bone. Doing the skeleton dance.
The inspiration behind this project is a current project that's going on in the QL Plus organization here at Cal Poly. In this project titled Cybathlon, we are building a mechanical exoskeleton for a man with quadriplegic cerebral palsy. The goal of this project is to help provide powered movement to allow this man to stand and walk instead of being confined to his wheelchair. In doing so, it is important to match how the body actually moves to avoid any sort of injury by conflicting motion or trying to force his body in a manner that would be harmful. Currently, I am working on the knee joint of this exoskeleton, and in order to accurately provide the correct torques, gear ratios, and motor selection, we need to look at the angular velocity of the knee joint and determine what speeds we want the knee to move at. As stated previously, the goal from these calculations will be to find the angular velocity of the lower leg relative to the knee joint. What we know for this, which would be known from a motion study conducted on an individual walking, would be the velocity of the person's center of mass, the length of their torso, the length of their upper leg, the length of their lower leg, and the velocity of their ankle. The unknowns that we would be needing to solve for would be the velocity of the knee, the angular velocity of the upper leg, and the angular velocity of the lower leg.
For this problem, we have to make a few simplifying assumptions. This is a two-dimensional problem, and the knee and hip joints are treated as pin joints. This assumption in 2D means that it is free to rotate. Looking from the torso to the mid-shin, we assume that they are all uniform rigid bodies. This essentially functions as a 3-bar linkage.
For the method to solve this problem, we would use kinematics, and we would set up a relative motion equation using the upper body and the knee joint. The upper body is one rigid body in pure translation, and so the hip joint would have the same velocity, which is just a velocity in the x direction, while the knee joint moves in something else, so it would have two velocity components, one in the x and one in the y. And the knee joint relative to the hip joint moves in a circle about the hip joint since they are a rigid body. In this problem, we're trying to solve for omega ak, which is the angular velocity of the ankle, in terms of omega hk, which is the angular velocity of the thigh. So our first kinematics equation relates the velocity of the knee to the velocity of the hip. And as you can see, we stated that the velocity of the knee moves in something else, while the velocity of the hip moves in a straight line in the x direction. And therefore, the velocity of the knee relative to the velocity of the hip moves in a circle about the hip. So then our next step would be to solve for the velocity of the knee, and we do that by plugging into the next equation you see, where we said that the velocity of the knee relative to the hip equals omega cross r. So in our second equation, we relate the velocity of the ankle to the velocity of the knee. And remember, in our previous equation, we solved for the velocity of the knee in terms of the angular velocity of the thigh. So in this equation, we say that the velocity of the ankle is also a something else. So it's going to have an x and y component. And the velocity of the knee we solved for before. And the velocity of the ankle relative to the knee will be a circle about the knee. So using those three parts, we can now solve for omega ak, or the angular velocity of the ankle, in terms of the angular velocity of the knee.
The thigh bone's connected to the hip bone. The hip bone's connected to the backbone. The backbone's connected to the neck bone. Doing the skeleton dance. Wiggle, 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 wiggle,